that's sort of the bare minimum that you will or may get asked in an interview sort of situation. And then I mix and match the rest of it. Okay, so it probably won't last longer than 20, 30 minutes, but let's see how it goes. Right, so first of all, data science. What's the point of data science in the modern enterprise? There's been quite a few debates about the relevance or how long data science has been in use in business. What I will say though, first of all, is there's a lot of fancy terms that's been that people use. So a good example is data analysis and data analytics. Now we'll talk about how that ties into data science. So data analysis is a good old-fashioned way of looking at data to get insight into various parts of your business or performance, primarily for the purpose of being more profitable or cost efficiency. Now, data analytics, in actual fact, is data analysis with a new name, effectively. It just means that in the old days, data analysis would have been done by mainly academics, statisticians, and people who would apply statistical methods to sort of provide inference that they are sure, they would have applied different techniques to verify the predictions that the various models would have produced. And data analytics is effectively the same thing, but rather than just have a bunch of academics or hardcore statisticians coming up with models and munging your data, it's now open to technologists and everyone. So from that sort of brief introduction, data science is really an intersection between three main disciplines. So first being software engineering, second being statistics or statisticians, and fourth being business people. Sorry, third being business people. So statistics, computer scientists or data engineers, and then business people. So now the prerequisite for this is obviously kind of ties into that. So I will show you examples using Python. And for your part, you only need to have basic understanding of linear algebra and statistics, and you don't need any knowledge of machine learning. So I'll try not to read from the slides directly. So what sort of people comprise a modern data science department, if you like? So you have the same usual suspects as you would in a sort of standard IT environment. So business analysts, developers, data engineers, DevOps, but only this time you've got data scientists who are sort of intersecting between the different roles. Now, primarily what the data scientists, in my experience, would do is you'd look at the data, come up with your deductions and inferences, discuss it with business, apply statistical rigor to your data and to your model, prove that your model is at least fairly accurate, and then you hand that over to the engineers who then build your model or bake it into the software, as it were. So a good example would be if you use Netflix or Amazon, when you buy something online, it tells you, people who bought this also bought that, for example. Or with Netflix, if you watch a certain type of movie, based on what people like you, that's in Netflix opinion, people who have the same sort of demographics as you, age-wise, maybe the time you watch films and the genre of films you watch. So for example, if you're into action movies and maybe it's 80s action movies, they sort of collate all that data and off the back of that predict, with this degree of certainty, what type of movie you may like or what type of movie people like you have liked in the past, and then suggest that to you. And obviously, when they suggest it to you, if you actually play the movie, they take that as feedback as well. So they use that to score the model which they've built to see how accurate it is. And things like if they suggested a movie and you watch it, did you watch it to the end? Did you just watch 5 minutes and just discard it? And all these things are like data points for them, which they keep harvesting and harnessing to A, score their own internal models, and B, just get more data about yourself. So from a point of view of the skill set a data scientist um, is expected to have from a sort of computational or technical perspective. So it's usually Python, R, SQL, SAS, and I'll try not to read what's on the screen, but I'm primarily focused on data science part. And what you produce essentially is just predictive models. You know, if we boil this down to its most basic essence, what's expected of you is you produce something that can predict something with a high degree of accuracy, and you minimize your errors, basically. I think that's enough for that. So another interesting thing about data science is I found this link from research done in 2016. In my opinion, that green section should be even bigger because you spend a lot of time. So building the models is not difficult, actually, because you have libraries that would do it for you. But you spend a vast majority of your time getting to understand the data, and you can't stress this enough. This is where people fall down because you may not be dealing with 10 rows, you may be dealing with 10 million rows, you know, or 1 million row, and you need to check certain things. You know, for example, if you're checking it, think of a table that's got maybe name, date of birth, and bank balance. You need to make sure the 10 million rows all the rows have an actual value that is of a float type, for example, something that minute. Otherwise, your model accuracy would just drop. You know, and so essentially, the job of a data scientist primarily first is to understand the data, cleanse the data, and manipulate the data so that it makes sense. Another example is you may have numerical data. So given the example I just talked about, say name, date of birth, and bank balance, there might be cases where the record kept for you isn't numerical. It could be text, you know, things like your local government, for example, that's a good one. Or, you know, your gender, would be male rather than one. You know, say for example, things that are textual in nature and you still need to derive insights from it. We'll get to all those data, but this is just a breakdown of this sort of time you'll spend on doing various tasks. And if you look at it closely, you find a building is only 3% and refining the algorithm is 4%. So collecting data sets and cleaning the data sets is what, nearly 80%. Right, so that brings us nicely to the next slide, which is you know, how you collect data. So obviously you collect data depending on the industry you work in for various things. So IoT is one that's really popular now. That's Internet of Things. You know, devices that keep broadcasting data to you. So an example of one of the clients that we are possibly going to onboard in Nigeria is they have sensors on their generators. They have sensors on their machines, you know, and that sensor will continuously send data into the cloud, you know, at various intervals. So that's an emerging, very popular data source. And then there's obviously different ways you can scrape data. You can get it from web forms, databases, APIs, and the rest of that. Now, I'm not going to spend time on this because this really is just a way of pipelining the data you need. Once you get through this, you then have to actually sit and work on the data. So the next slide is, this is again another fun fact I got, that we produce on average 2.3 trillion gigabytes of data per day. It doesn't sound very much now, but if you think about it, trillions of gigabytes per day. So there's lots of data and there's lots of work to be done with data. So collecting data might be a problem, but producing data is certainly not. Now the data science discipline has a few processes which you would have to go through essentially in terms of, if you think of a software, if you're a techie person, think of the SDLC. This is the equivalent of it for data science. So you collect data, you arrange and organize the data, analyze the data. This is where, and this section where you analyze and model the data will be very iterative. So you keep building the model and keep testing your model. So a good example is, say you work for a bank and you have a lot of data. You want to know if somebody will default on a loan. So, I mean, that's a popular example. So what you do then is you keep building the model and testing it on your back testing it on known data to see the performance of your model. You spend a lot of time iterating, going back and forth around the analysis section. And it may well be that at the point where you're arranging and organizing the data, if you make mistakes there, if you don't clean your data or extract the right features, then you're not going to get an accurate model. So again, it's very important to spend good time with a domain SME, subject matter expert, or a domain expert, because it's often not technical. So I'll give you an example where if you've got time as a value in a table, for example, and you're trying to build a machine learning model or some sort of predictive model, that's got to do with time. So say, for example, the probability of something happening may be higher in the afternoon than it is in the morning. Now, you may have that time, but if you don't get that information from a subject matter expert, the model will just try to build something based on, say, an equal probability for the 24 hours in that day. So things, minor things like that, that makes a difference to the business. You need to incorporate that. And this is why I said it's an intersection between business analysis, between computer science, statistics, and business. Please let me know if I'm going too slow or too fast so I can speed up. Yeah, I'll send the slides and the code afterwards. Now, so Python tools that, yeah, this is the primary tools that people use, Anaconda being the Python environment. In terms of accuracy, that would be 20% accurate. So you can build your machine well enough to the point where it gets to 80% accurate. And this is what happens in fashion houses. I worked in one where we use predictive models to the point that we know how much you're likely to spend if we send you a voucher. So we don't send vouchers to everybody. We send it to people that we know are likely to spend. And we then track the use of it, and we see that they do spend it, you know. But that's essentially what supervised learning is. You label the data and get the machine to train on labeled data, then you give it unlabeled data and get it to produce and compare what it produces with your known value. Unsupervised learning, on the other hand, it's a more complicated thing where you don't know any trends, you don't have any idea, you just give a bunch of data, you connect your predictive model to data, and the predictive model by itself tries to seek out association. So things like neural networks, you don't have to tell it Tillman spends X and Y. It just looks at the data continuously and starts to deduce that by itself. So things like self-driving cars use an advanced version of, say, neural network called deep learning, which is it learns and then it relearns itself and relearns itself. And you don't, sometimes you give it images to start off with and then it starts to learn later on by itself. So what I described to you about the labeled one is an example of, a typical example is when you look in your inbox and you get spam and normal email, it uses information it knows about what email is not spam and what is spam and uses that to filter spam emails out. And 9 out of 10 times it gets the spam emails right. So that's a typical example. And things like Siri and Alexa, it lends your voice, and those are similar type of models. So these I've described already. You give it data it's seen, and then you then pass unseen data through it and then see how it performs. So that's, you pass a test data set, and again, that's described with the same thing. So using the spam email example, this is how the table would look like. You have a sender URL, the kind of text, where it's coming from, blah, blah, blah. And then you label it as spam, real, spam, correct, correct, incorrect. And then over time, the machine learning models learns what's likely not to be correct. Again, that's that essentially. So what I've described to you so far about giving the machine something and it's predicting something out to you, that is, there's a name for that type of model, or that's called a classification. Basically, classification is classifying is when you're trying to predict something that's discrete. By discrete, I mean trying to find a continuous variable like regression. So an example is, let's say we want to find out who's likely to go to church on Sunday or the mosque on Friday. There's a finite number of outcomes. They're either going to go or not going to go. Okay, so that's a classification problem. We're trying to classify what decision the person takes. That's one type of problem. There's other types of problems that I say continuous. So an example of continuous or regression problems are, I want to find out what the stock price is tomorrow. The stock price tomorrow is not a binary thing. It might go up by £10, it might go up by 100 naira. So that's a different kind of problem. So in general, when you're given something to do, so you have to identify the kind of problem you're trying to solve. Am I trying to solve a regression problem where it's continuous variable, the data keeps changing, or a classification problem? Another example of classification problem is people have come to borrow money from the bank. If you want a loan, they're either going to default on it or they're going to maintain good credit. That's a classification problem. You know, a lot of problems you will encounter would be classification and regression problems. There's many other types of problems, but these are the two popular things you need to solve. So the example here is of the Titanic again. I don't know if many of you have heard of Kaggle. Kaggle is the online platform for data science learning and machine learning competitions. And the classic problem we're trying to solve is people who may or who have or who did survive the Titanic. You get a data set, which Kaggle gives you, and they have their own test set, which they never show you. So you keep building models, you upload your model to Kaggle, and they give you a ranking. So for example, you might be, you know, number 1 or number 150,000. But the reason I mentioned the Titanic is because that's the example Kaggle, most people start with Kaggle. And this example here is showing class survived as 1, not survived as 0. That's just saying this is a classification problem. We're trying to classify whether the person survived or not. And like I said before, the other type of problem is a regression problem where it's continuous. You know, it's not a yes or no. It's a how much is it going to go by up by type of question. You know, how quickly, how much. It's not a case of a plant or a generator. You look how much. When is it going to break down? Is it going to break down soon? Is it going to break down in the near future? So there are some problems that are a combination of a regression problem and a classification problem, which is interesting enough. A lot of problems are like that. If you first of all want to classify something, again, will stock price go up or down? Is one question to ask. But the next question is, how much will it go up by? So from that point of view, you could look at it as a classification problem, if that's what you've been tasked with at work. But then from a different point of view, you want to know how much is likely to go up by so that you can determine how much you invest in that particular security. Another type of machine learning algorithm is clustering. And that's primarily used for customer segmentation. Again, this is very popular with unsupervised learning, where you know, maybe the machine looks at a huge data set and it starts to identify certain customers. Maybe with Amazon, maybe some people buy more electronics and some people buy more books and stuff like that. And then you can segment customers based on these attributes or features that it, you know, nobody sits around on tables and starts saying, let's put this feature on the table. You know, most of these websites have things like Kafka now. Everything you do on the site, they stream it straight to the database. If you click this, click that, everything is going there. They just collect data like there's no tomorrow. So that data, they can then make use. You know, they know who you are on the site, and they've collected your browsing habits, what time you browse and how much you spend. And they can use that again to, if you like, segment you as maybe a high spending customer or a once in a Christmas type spending customer. And then they can then, this marketing department can then use that data to get you to spend more money. Clustering is also a very common algorithm. And again, it's used for, you know, you can use it to separate customers, you know, looking at demographic features and previous purchase history, and then even what kind of movies you watch on Netflix, those kind of things can be used. I've talked about regression quite a lot. I just thought I'd put a little slide there to just reinforce it. You know, what you're trying to do is you're trying to draw the best fit line So going back to the students in the class that did tests, that's over 100. Sometimes we just want to be able to predict how these students are going to perform next year based on some feature. Maybe, Mr. X or Mr. Adewale was the one who taught them, and then Mrs. Johnson's teaching them now, and we're trying to check the teacher's performance based on the student's score. So we can try and predict, like what they're likely to get next year. So for example, going to university in some countries, they give you university places based on your predicted grades. You get the place before you finish the exam. So this is a good candidate for that, where they can look at all your previous marks and who's taught you, and then they can almost project what you're going to get, and off the back of that, they can be reasonably confident if the model is 95% accurate, which there are models that are out there that are maybe 90% accurate, 92% accurate. In fact, 95% accurate, Microsoft's voice, so-called voice typing software is more accurate than human beings. So regression really is about finding the best fit and trying to connect continuous variables. There's a lot to talk about regression. We spend like a year on it. There's different types of regression. This is an example of linear regression. This is logistic regression, where you're making a binary sort of choice. So look at the previous one. This is a regression task, right? There's different dots. You're trying to connect them differently. Notice the next one is a binary classification. This is somebody trying to get a loan. Again, it's a regression problem. It's a different type of regression algorithm, logistic regression. There's a lot to learn about regression in general, but I would recommend, if you're learning on your machine learning journey or data science journey, just focus on one. Focus on classification. You can't go wrong, or linear regression. And once you know those well enough, everything else starts to fall in place. I think with that, we'll come to the end of the slide. So what I would have liked to show you is building a machine learning model and tuning the model, and also how to save your model. But I don't know if we've got time. Let me see if I've got 5 minutes to show you a few more things. So I think that's it for the slides. I'd just like to show you some things on fire. I'm just trying to get some message from how much time I've got.
As an introductory session, I think it did justice and went very deep in data science. And I think everybody was quite really engaged in the session, because the replies were coming fast and as you were requesting for them. And so, yeah, let's do the, you can quickly run through the model and just share the screen. Let's have a feel of that before we go into the Q&A. Okay, so while we're setting up that, guys, if you have any questions, please just start putting them together, so that once we're done with the run through of the modeling, then we can start answering the questions immediately.
Yeah, I think I lost you there for a minute. Can you? What did you say? I kind of missed out on.
Okay, I was just saying that you went very deep, as much as it was an introductory session. That you did quite a lot, and it was a very extensive session. And then, yeah, we can quickly run through the model that you like to share. You can just share your screen and we'll run through that. And then, whilst we're doing that, they can prepare the questions and you take them afterwards.
Yeah, I think I'm happy to take the questions as I talk you through this one. So depending on the nature of the question, but yeah, I'm okay to take that question. Let me just share my screen.
All right, so guys, if you have questions, let's start sending them in and we can run through.
Share my screen. Okay. Can you see my screen?
Yes, yeah. Okay.
Okay, so it's a bit of a funny on this one, but so this is a Python book, and some of you will be familiar with it. The data set behind this is the Titanic data set, and it really just contains things like I'll show you the data, but things like the age, the class of the ticket speaker boards, the gender, the embarkation points, that sort of stuff. And this is a very common data set which you can get easily from the internet, and it's a good one to get familiar with because it's nice and easy and simple. But then you go through these normal steps anyway. Let me run this. Right, so the primary tool, I told you about Panda earlier on. The primary tool you use in your data analysis journey in Python would be, there's three things, NumPy and Pandas. Now, don't worry if you don't know Python. So think of Pandas as an Excel spreadsheet, right? That's got rows and columns. That's essentially, it can store more than for our and for your purposes. Just think of it as a big spreadsheet in Python. So now these things here, just opening the spreadsheet. So I'm indexing it by column. I'm opening a spreadsheet for test and train. This is stuff I've prepared in the background. So this train DF, can you see that? Let me see if I can zoom in. Okay. So this train DF is train data frame. The data frame is the Panda data frame, and that's essentially, you can see the data type. It's a data frame. Think of a data frame as an Excel, like a table. Okay. So if I run this here, just to get the data type, it tells me it's a data frame. This is a useful method in Python info. It just tells you about the data frame. So these are the columns. If you look at it, it says data column, survived, passenger class, name, sex, age, tickets, fare, cabin, embarked. Okay. So this is my test data set. It's I spoke to you about splitting things into two. So you have a train and a test data set. Again, if I do info on that, it gives me the same column names, but okay, so you see the data types here. Just notice that the entries here is 891 entries. You see that? That's for the training, and the test data set is 418. So if you look at it, Python is really helpful. It tells you that this data is from number 1 to 891. This is the training data set. And the test data set is from 892 to 1309. So we've sliced it into two, okay, to see how good it's breaking. Now remember, this is the name of the fields. P class, name, sex, age, and the rest of that, right? So what I've done here is everywhere I've created it. So let me show you, I need to show you this to make it easy. Okay. So IPython notebook, you can just literally just add a cell to find what's going on there. So let me open a test data set. Just type that in there. This is what I'm saying, how easy Python is. You just type that in there and just click on run, and then you just open the data. You see? So this is the data frame. This is what was read from this spreadsheet. Okay, and this just gives you, when you're doing your exploratory data analysis, this gives you an idea. This is the passenger ID. This is the class. This passenger has third class. This Mr. Kelly, Mr. James Kelly, which is his name. Third class, purchased a third class ticket, and his male, his age is 34.5. That's his fare. And you see this NaN thing here. You're going to see that a lot in Python. This is the number not available. It's like it's called NaN basically. You don't have the value essentially, not a number. Sorry. And then this is you do this to just get a feel for the data. And you see this embarked has different codes. So I think S might be Southampton, and then Q, I don't know, maybe Quebec somewhere, and C maybe somewhere in America. So this, you just literally do that, and it shows you the data just to have a feel. Now, another thing in Python is looking at the data frame. So remember, the data frame here, anything with DF is a data frame. I'm just giving it test data frame and the train data frame. So, and literally, you see this survived here? Just this line literally just adds a new column to the spreadsheet and adds this value into it. So if you look at this now, you see, do you see any column called survived? The answer is no. But obviously when you go, it's added that column there. So if I were to run this again, you see that at minus 888, which is what I did is added. So that's how easily it is, for example, in Python to add a new column to your data frame. Again, to understand your spreadsheet, I'll just call it spreadsheet, not to confuse you, but just to kind of cement the concept rather than confusing you with a different name. A data frame is like a spreadsheet, so let's just call it that for now. It's more than that, but let's just call it that for now. You know, if you call the info command, it tells you about the data types. You know, if you don't, I don't think you need to be a programmer because a data scientist isn't considered a programmer. In fact, they're called rubbish programmers. That's what they refer to them as. It's just to know enough to be able to deal with your data, you know, so it doesn't get in your way. There's this option here to do df.head. So what that does is it shows you the first, if you don't want to see everything, because you could have 100,000 rows, df.head by default will show you the first 5 entries in your spreadsheet. And then if you want to see more than that, you put a number there. So this has got 10. So if I want to see the top 100, I can just put 100 in df.head and it will just, you know, there you go, just show me 100 items, up to 100. This is just me playing with the data. Then if you do tail, it shows you the bottom item as well. You know, head shows you the top 10, tail shows you the bottom 5 as well. And then I have a column there called name. So the way to access it, if I just do df.name, this is basic Python, by the way. I hope people are not feeling it's going too slow. I'm just assuming some people don't know about it. So if you do df.name, this shows you the details in that column, you know, the name feature of the passengers. So you can either access it by doing df.name, or another way to access columns is using a square bracket and putting that reference in there. And that will give you the same thing. Again, instead of looking at the whole spreadsheet, if you just wanted to see 2 columns in it, you could just specify the names here, and it just shows you. So if I wanted to see the survive that I added, I would just say that here, and that would just show me. This is what you have to do every day to get a feel of your data and to understand, you know, to spot things. So there's various ways of accessing things in Python. Anyway, I'm not going to bore you with that. So you can, you know, go through the first 5 rows and the next 10 elements. Just, it's got all this nice ways to look at things. And then you can search. So for example, I'm creating a new data frame here just by saying, give me where all the data frame.sex, the column with sex that is male. I want you to create a new data set called male passengers, right? So if I run this, it's not telling me of all the people in data, there's 843 males. Again, I could do the same to say, give me the value where they're male and their passengers are first class passengers, and it should give me a count, 179. So what I was saying about summary statistics in Python, so just by using the describe keyword, it would give you a mean, standard deviation, mean, the range, and the quartile range of everything in all your data if you want. So this is for the whole spreadsheet. So it's going through all the different columns and working out the counts. First of all, so I've got 146 data points for age, 1300 for fair, and then it just gives me the mean, the standard deviation, and max, and the rest of that. Again, you could just, if you wanted to, just call the column name with mean, and it would just return the mean, essentially. You don't really need to worry too much. All the stuff has been built and baked in. So you can get a host of things like, you know, the standard deviation, the quartile ranges, percentiles, and then let's go to visualization. So there you go. So let's clear this first and let's rerun this. Okay. So now this is a box and whisker plot. You see it appears that there's a lot of outliers at the top here. This is a box and whisker plot. I don't know if you recall what I showed you earlier in the slide, but this is just checking the fare. You know, so somebody paid £500 or something for the fare. This is someone, I don't know who they are. This gives you an insight that maybe there's, I don't know, a rich millionaire on board or somebody bought the ticket last minute just before they went. But you can see that most people paid around £100 mark for it. And in fact, the median point is less than that. Yeah, this green line. Again, with categorical variables, because you can't get mean, median, and mode, you can have like counts. So for example, here, the data frame, I've just said df.sex and count. And then by itself, it comes up with the number of, based on the sex column, number of male and female. And what you can also do, so another thing with machine learning models or predictive models is you don't really want to pass crazy values into them. You don't want to be passing 2,000, 5,000. You want to normalize the data. So you've got to make it proportional and representative. In the case of stock or asset return, if prices go up and down, let's say Google's, I don't know, say Facebook is $179 a share or something like that, and it becomes 180 tomorrow, 190 tomorrow, you don't want to feed all that to your machine learning model. What you want to do is you want to take all the variations on a day-to-day basis, -5, 3, and then work out the returns. Okay, the return on your investment there's a standard Python way of working it out. Then you might need to find the log of those values or normalize it such that it falls between 0 and 1, if that makes sense. So you're trying to find the variation or fluctuation in the prices rather than looking at one individual prices. Because what you want to predict is the fluctuation in the price and the degree to which it fluctuates, rather than it's going to be £200 or $350. You just want to predict that fluctuation. So the normalized thing here, essentially, as just said, 60% of the passengers are male and 35% are female, but it's just brought it down into less than 1. And it's easier to fit this into a predictive model than to say 695 or 492. Again, we can use things like value count for categorical variables. This is doing a count of where survived equals -888, which we added at the top. So value count. Now to plot, so this is interesting because this P class is the passenger class, right? And the passenger class, as we know, is not what is it? Let me have a quick look at the passenger class. Okay, so passenger class is numbers, and then we can easily plot just by calling plots, which is a matplotlib is a Python library, calling plots, and that matplotlib has been built into, or pandas can call the plot function directly. So think of this as an Excel spreadsheet where you can put data in and plot and choose your own graph, but this time you're a data scientist and you're working on insights rather than relying on Excel to do it for you. Because a lot of these things can also be done in other tools, okay? Not necessarily Python. You can use things like IBM SPSS. You can use third-party proprietary tools to work out regression and to select variables and to convert categorical variables. But this is what's used in the industry. So you kind of have to go with trend. So anyway, just calling this API, you can plot graph, and what I said earlier about looking at graphs, pictures is much easier and it makes a lot more sense to more people than just giving numbers. So here you can see most people were where 700 people were third-class passengers, and a good proportion was first class, and another slightly smaller portion were in second class. Again, so we talked of distribution earlier, right? So now this is a histogram. This is a little bit like that distribution, but this time is a histogram, and it kind of shows you the same thing, but histograms use bins. Bins is basically, if you have 1 million data points, you can't plot 1 million into a graph. The graph would be crazy. So you kind of slot them into little bits, like maybe 1 million per bin. And then instead of having 20 million, you have 20 bins, and each bin has 1 million. So this histogram has 20. You can choose the amount of bins you want, for example, in the histogram to make it smoother. So you see this histogram at the top here, and run that. is the same as the histogram at the bottom here. Let me see. But then this has got a bin of 20. So I could change the bin number here to like say 40. Yeah. You see, it has a different feel to the graph, like it's more smooth. So I could, just by increasing number of bins, I could see maybe get some more insight into the data. Like, okay, over here, I can see there's, there's an extra, there's a drop here, which you can see here, but not quite as much, and then like, I don't know, you can really go crazy with it because, you're just trying to find something. You see, I've compared it to 100 bins and it's too much and it's not optimal, that kind of thing. You then play around with it. And this is, a distribution density, kernel density, KDE plots, basically. It's exactly like that one, but this time it's more smoothed out. And this is the skewness. So the skewness that I've described before in the distribution for age is 0.41 and for fair is 4.37. Depending on what you're doing, if you're not doing financial analysis, the skewness may not matter to you, and then the inferences you draw from the skewness also based on your knowledge in that particular industry, about the data. So this is skewness just for the fair. I might want to plot skewness for the income distribution of ladies living in, say, Bagada, that's between the age of 20 and 40, just to see their salary and see where they're likely to spend their money. So you can think of loads of different things you can do. So I won't bore you with the rest, but this is the things like group by thing. You can group by. You can do pivot tables. You can do crosstabs to get an idea. You can put different things together and have a third thing work out as an indicator. But this is an introductory course, so I think it's probably okay at this point. Although there's, I mean, if Cousant are interested, I can do a follow-up session where we actually build a simple model and we score it for accuracy and stuff. There's a lot more things to talk about, things like there's something called a confusion matrix, which when you're building your model, you try and work out, false positives and false negatives and try and identify. I mean, there's a lot of rigor and discipline that's been built into these models on how you build it to the point that you can, to a high degree of certainty, rely on your predictive model's output as Excel spreadsheet, a database with 3 million rows and different tables to make sense. So the first thing you do, obviously, is to make sense of the data, which goes back to that slide. Let me go back to that slide. This one here where I've got arrange and organize. You need to make sense of the data. It's a little bit like understanding your requirements before you start writing code if you're a developer. So EDA is what you do first, and essentially just to keep it simple, the few things, sort of rule of thumbs or tutorial type things you get is you want to understand obviously how many rows you have in the table, the most important table that you're looking at, how many columns. It sounds simple, but so we describe columns as features. So if we go back to the example I gave previously about the bank and your bank balance and maybe your local government, things like your local government, your gender, those would be considered features because they would matter, in what we want to predict eventually. So using Python, you can deduce, you can have a quick look at the features or columns, the rows of observation, to know how many rows you have. You can look at the data types to make sure the bank balances are on, to see if it's what format the bank balance is in and if you need to convert it to the right format. You also get summary statistics, so things like mean, median, standard deviation, that sort of stuff off the bat with the Python tool, because the Python tool use. So Python has a library called Panda, which I will get to later on, and it's as easy as just dot mean, and that will give you the mean of your data and things like that. So the other thing you do is if you have categorical data, so just to make it clear here, categorical data is what I described before. It's data that is not numeric, things like your local government, for example, or your gender or things like that. And numeric data is obviously numeric data like bank balance and date of birth, that sort of stuff. So the first few things you do is you do an exploratory data analysis. So we're going to go further into that now. The other thing you get is you get the distribution of your data set. You can group it to see, correlations, observations, and to try and deduce causation. Okay, so so I want to talk about the basic things first. So mean, I don't know, we should all remember this from school. It's important. It's one of the first few things you do. So again, what if we don't know how to code? That's fine. There's not much coding, to be honest. And the slides, the Python notebook slide, you don't really need to install anything. Okay, let me just describe it. So if you don't want to install Anaconda, there are free versions of Anaconda pre-installed on somebody's server online that you can use. I've just to simplify it, you can go to Microsoft Azure, set up an account, and you have free notebooks, and you can test the stuff yourself. And you don't really need to know how to code. You can just literally click run from what I give you, and it would work. But then it will all make sense as we go towards the end. I think I need to speed up, actually. So again, mean is, we know what the mean is. Mean is, that's the formula for mean, basically. Add all your data points divided by the number of points, and then you get a mean. The problem with mean, and in statistics, is obviously it's very prone to anomalies or outliers. So, for example, if you've got 10 kids that are all 10-year-old, and you do the mean, you just add the 10 by the 10, which is 100, and divide it by 10. So the mean is 10, and that gives you a good indication of the age of the kids. However, if you now add someone that's 90-year-old to it, what that does to the mean is it throws it off. So you suddenly have from 100 to 190, and you still have to divide it by 10 if there are 10 people. And then the mean just changes drastically. So the mean by itself is not a reliable indicator of the spread of your data. We also have the median, which is, again, you order your sets or data set and find the midpoint. And if it's more than one, you just add it up and divide it by the number of midpoints you have to get it. So median, again, is just another one of those things. It's not reliable. You can't use it, but there are times it's useful if your data set is evenly spread out. Okay, and then range, this is basically the difference between the highest or the largest value in your data point and the lowest value, just to give you, again, an idea of the spread. So using the example of 10-year-old kids, so you got 9 kids that have 10 years old, and the 10th person that is 90 years old. In that case, the range would be 90 minus 10. So there's an 80-year gap between the oldest and the youngest person. That just gives you an idea of the data you're dealing with. So that's the formula for it, and that's the diagram for it. Now, percentiles, again, this is from school. I'm sure some of us will remember this. So this is just a breakdown of, again, the spread. So these measures are measures of centrality. You just want to know where your data sets, where they sort of cluster, if you like, where they're all centered around. So it may well be that everything is centered around the middle, which is the mean, but you might have clusters. So you might have a cluster of data sets spread at a 20% point and at a 50% point at a sense. So it's good to use things like percentiles to know the spread of your data at different points. So we've got this box and whisker plot, which supports the percentile measure, and what it just shows you at the very bottom is the minimum value and the 25th percentile in the interquartile range. 50th is the line in the middle, and i.e. the median, and 75th is the one at the top. Now, the little dots at the top and the bottom, these are outliers. So again, think of the ages of the kids. So the man who's 90-year-old is an outlier because the majority of the data points is spread around, 10-year-old sort of mark. And then if we were to plot that example, the dot at the top would be that 90-year-old man, and then the bulk of the data will be spread around the mean. So this is just a way to visualize that, basically, percentiles. And it just gives you an indication straight up the bat that, I have, just in case you have a lot of data that's, spread around to the 25th percentile, then you know that maybe that 25th percentile mark might be the times customers come to shop, and you're collecting data about customer entry points. So, this is somewhere we need to look at. This is the interesting beast. This is a feature that we ought to maybe investigate a bit more than the rest. Okay, the next measure is variance. Variance really is to do with the, surprise, surprise, measure of variability. So it's a very useful indicator. It's perhaps the most useful indicator, even as a basis for going forward. So it lets you know the variance in your data set. If you have large variance, then obviously the spread is huge. And if you have a small variance, then the data is they're not too far apart, they're tied together, or they're a bit closer around the mean. And the way I said the mean is affected by outliers, the variance is less susceptible. I can't pronounce the word. It's not as susceptible to being thrown off by the mean. So the variance is a better measure. Now, the way to work out variance is essentially that yellow line, if you like, orange line, is the mean, and those dots are the points, the different points of your data set. So let's think of it as, again, scores in a class. So you do a test and it's over 100, and people get different marks, 10 over 100, 50, 70, 30, 40, and these are all the data points. So these are essentially all the scores from that test by all the students. Now, the orange line is the median. So, middle sort of points when you add all the scores and divide it by the total number. Now, the way to work out the variance is the difference between each point and the mean. So sometimes there's something called the mean squared, which is so the distance between every single point and the actual mean of your value. You summarize, you sum it together essentially and divide it by the number of points. You square it and divide. You find the difference. You square the difference. You then add all the values and then divide it by the number of values. That makes sense. So now, typically, there's something called a Bezel correction. In the real world, if you were to say, for example, get a cross section of height of height of men in Nigeria, for example, there's usually you usually have to do that -1 to improve your variance, and that's known as Bezel's correction, and it's something that's quite common and used widely. Again, standard deviation is a measure. It's the square root of variation. In financial analysis sort of terms, the standard deviation is also a measure of risk. So it's a question of how much you deviate from the mean. I'll come to that with another diagram in a bit, but just think of it as variance, the square root of variance, basically. So there you go. That's the formula for variance, and that's standard deviation, the square root. Now, that Gaussian distribution, so everything kind of ties in together. I was talking about having a measure of centrality and dispersion and the rest of that. But this Gaussian distribution is otherwise known as the normal distribution. It's usually also called the Bell's curve. So, and this is, so to give you an example, that little curve is, so you got 68%. So mu is the standard deviation. Sorry, mu is the mean. Sigma is the standard deviation. Yeah. So if we were to take the height of all men in Nigeria, for example, it should fall under a normal distribution. And what this means essentially is there would be a mean. Let's say the mean height for men would be 5'8" or something, or 5'7". So that would be that line under the mu sign. Now, you see there's a mu plus sigma and a mu minus sigma. That is one standard deviation from the mean to the right. That's the mu minus sigma. And one standard deviation from the mean to the left is the other one. So between those 2 points, sigma plus mu and sigma minus mu, you would always find 68% of the population fall under that area in the curve. Now, you see that little line on the side, that's two standard deviations from the mean, which means that, for example, if the mean was 5'8", right, most people would be, so that would mean that that's the average height. But then 68% of Nigerians, for example, would then fall within, say, one standard deviation of the mean. So that would mean either way, you have some people that are maybe, for argument's sake, instead of being 5'8", they're 5'9" on the plus sigma side, or they're 5'7" on the minus sigma side. So it's a question of how far away they move from the mean, from the middle, if you like. So you can think of it in terms of monetary terms. So let's say the average salary in Nigeria is, I don't know, 2 million naira or 1 million naira a month or whatever. What you would find is, again, that would be the mean. And then one standard deviation from the mean could be maybe some people earn 1.4 and some people earn 600, and that would be 68%. So basically, that's one standard deviation from the mean. If you move to 3 standard deviations from the mean, 99% of the population will fall under that. So that is a normal distribution, a Gaussian distribution. Now, there's different types of distribution, but this is the naturally occurring thing. So if you took maybe the weight of babies in one state in the east and the weights of baby in another state in the south, providing all things being equal, they would also fall within this sort of distribution in terms of sizes. Just ignore the formula. The key thing is to understand this distribution, because you're going to have to deal with this distribution a lot. So again, think of stocks and shares. If you plot a graph of returns of, say, Google, you're going to get something close to this, but then you would find that it wouldn't be as evenly distributed as this is. It might be more to the left and more to the right. So for example, if it's more to the left, if you're a financial analyst, that's telling you something, that's telling you potentially there's a higher chance of an extreme thing occurring, negative event occurring. And maybe if it's more to the right, it's telling you there's a high chance of something positive, like excess returns. Okay, another point from this sort of, we're about to get to the end of this stats bit, so just bear with me. So skewness and kurtosis, again, very important point. So kurtosis is a measure of how often extreme values on either side of the mean occur. So in Python, when we run the code, for example, let's say we take Nigeria, Naira and dollar exchange rate over a period of, I don't know, 4 or 5 years. If things are normal, when we run a check, look for the kurtosis, it should be 3 if things are okay. Now, there was a financial foreign exchange crisis. If we plot for the kurtosis at that time, we'd find it be in the minus region, which means, so excess kurtosis again is what financial analysts look for in terms of returns, which could potentially indicate the riskiness or level of risk you're dealing with at that point in time. So during the 2008 financial crisis in the West, if you plot kurtosis for the kurtosis, it was all in seriously minus, 3+ regions. Now, if you take that time out of all the returns of, say, the FTSE or the Dow, you'd get standard kurtosis. But for that period where things went wrong, you'd get the excess kurtosis. So it's just good to bear that in mind in general. And it's also called tail risks. So again, high kurtosis implies extreme event is more likely to occur. And that's the example of the 2008 financial crisis. Skewness, on the other hand, is a measure of symmetry around the mean. So you could have skewness in a positive sense and in a negative sense. So if your skew is positive, it just means, so a good example is if you plotted people's incomes, average income, the skew will be positive, which means there's obviously less billionaires than there are normal people. So they're tending away from the average to the right, if that makes sense. And again, that's negative skew. So it depends on the industry. So in insurance, for example, this is important because you want to know, based on data you've collected over the years, how likely something something extreme will occur, like a storm that might take out loads of houses and you have to pay out. And then that helps you adjust the premium you charge people for it. Okay, so statistical tests. So I've said quite a bit about basic statistics. These three tests, I think it's important to know about. One's called the R-squared test, the other's called a t-statistics, and the other's called a p-value test. And essentially, without reading the slide, I think R-squared it gives you a degree of confidence about your prediction. So if you think of a regression line, let's go back to the scores of student in the class. So the score is over 100, and then it's dotted around the base. Now you try to draw a line, to fit, to see how, to see the trend, between, say, the scores that students get and the income or the financial background of the parents. Yeah. So you try and join the line to see if there's a connection, if there's any kind of trend, because as a data scientist, right, you're trying to look for insights that can be profitable, either financially or in a social sort of enterprise where you want to help people. So the R-squared test is a measure of how well you're fitting your line around the dots to see how accurate it is. Now, R-squared is basically a measure of the error, the residual error. So if you build a predictive model, if you get an R-squared value for it, and then if you test your predictive model, you also want to do an R-squared test to see if I'm building a model based on known data that, okay, Olu, always comes home at 7 o'clock, for example. So you plot the chart, is always home at 7, and then you run your model. Yeah, that would predict 7 because you know about it. What about Olu's neighbor? So you also need to then plot the R-squared on the new data set or your test data set or the real world data set to make sure that your model is performing well in terms of how it's joining the dots based on what it knows and based on what it's going to predict in the future. I'll leave the t-statistics, I'll let you research it, but it's just, again, t-statistics help you compare means of two groups, for example, male babies and female babies, and tells you if there's any statistical significance or enough for you to, warrant a new hypothesis. And p-value, again, is a measure of no significance. Usually if it's under 5%, then it's not statistically significant, but if it's over 5%, you then have to reject the hypothesis. Okay, I'm going to try and move faster now. So again, going back to the bigger picture of data science, why you have to really understand the problem you're trying to solve. So if you're going to start, potentially looking at maybe a career in data science, I'd implore you to just choose an area that you find interesting. It could be something as simple as the frequency of electric supplies in Nigeria. I'm sure you can find the data somewhere online, or you can have an IoT device on your meter and start collecting it. And something that matters to you that you're a subject matter expert on. So you need to pose a problem, a real problem that's solvable. And obviously, in order to solve a problem, it has to be measurable, because otherwise, how can you tell if you are making progress? So understand why you want to do it as well. We're doing it to make X more efficient or X more profitable. And what is it we're looking for after? Okay, we want to save this company money on diesel. So it's very clear. So we start to look for what correlates with high diesel spend. So be very clear about the problem you're trying to solve. And then understanding your data. Previously, I alluded to the point that oftentimes when you get data, it's never clean. It's never clean in actual fact. There's always, for example, in the field where, using that bank balance example again, you might come across somewhere, maybe, I don't know, field 300,000 and row 2,000, for example, and the bank balance column, you might just find XTYT. That's not a number, and that can really screw things up. So you need to spend time understanding Python API to look through. Python has really easy ways to do that. You can tell it to look through an entire column. It doesn't matter if it's a million rows or 200,000, and to look up anything that's not numeric, and it will tell you. And you can ask it to convert it to numeric. Or if it's something that's not convertible to numeric, you can ask it to replace it with a null value. And if you don't want to replace it with a null value, you can ask it to automatically drop it. So in one line, you can drop all the, if you like, rubbish values in a million rows using Python. I mean, I've just exaggerated a little bit. I just want to take a checkpoint here. Are people following, or is it, what's the pace I'm going at? Is it fast enough, too slow? If you send something on the chat just so I get an indication. Okay. I thought I was moving too slow. Okay, so outliers, I think I already spoke about before. In order to make good predictions, you have to, sit down as well as the data scientist, you go speak to the executive team. Well, not on outliers, but you go and speak to the business matter, subject matter experts and say, look, we've got this outlier, a couple of things. Is it important? Going to the example of kids that are 10-year-old. The 90-year-old man is an outlier. Maybe your customers are kids of 10-year-old, and that's what matters to you. But you got this 90-year-old man that's making the data very skewed, and just so you may make the decision to exclude because they're not important. In actual fact, there are different techniques for handling those kind of things. You might want to take samples. You might decide that we need those outliers in there, but then the question is, what value does it add? Maybe I'll give you a good example. So if those 10-year-old kids are your customers, most of your customers, it may well be a case that yes, they represent the majority of your customers, but maybe the proportion of your customers who spend the most are people that are in this 70 and above category. So then it's important to keep those people in it because they're the ones that will make you the most money. You can only deduce this kind of data by sitting with the business analyst or subject matter expert. Because as a data scientist, you just think, look, we've just got this anomalies that are just really skewing up the model. Let's just get rid of it. And then you would get rid of it. It would work well for you, but not for the business. So again, focusing on requirements, that's key. How you deal with outliers is a matter of what the subject matter expert thinks, but technically, when it comes to just handling that in Python, there are ways to just drop stuff that you don't need. Okay, so far, we've talked about the different statistical measures with which you can look at your data in first exploring it before you start thinking of what to do. So when you're through with the exploratory data analysis, at this point, you figure the mean age of your customers are like it's 10-year-old. You figure the mean salary is £40,000 or 1 million naira. You figure that most of your customers are under 15. So by doing this exploratory data analysis, you're getting insight into the data. So this is the understanding your data bits, knowing this is what's missing, this is what we have, this is what our demographics are. So at this point, what you'll be doing is you'll be doing visualizations. You'll be drawing charts based on the data, and it'll be telling you different things, and then this is where you're having that conversation. This is what I'm saying. You spend like almost 80% of your time going back and forth, cleaning the data, getting insights, making assumptions, going to the business. They're going, no, that's not what we want. We don't care about customers that live in this part of Lagos because their income is XYZ, but we want customers of this income category, blah blah blah. And it's not so much what's right or what's wrong, but what's required. So feature engineering, once you understand the data, you've done your exploratory data analysis, you're fairly confident, you have a good feel and sense of, okay, this is what I have to work with and this is what the client requires. Then you have to start building features. I've just put a feature definition there, again, verbatim. I've tried to use this simple phrase to describe it. So essentially, think of features as rows, like I said on the table before. But those rows are important to the model you want to build or your predictive models. So again, if we find that women spend more on clothes, right? And there's a row that's got gender in it, we know that's an important row. Okay, so the way to think of this is when I talk of predictive model, what I mean is some sort of machine learning or some sort of statistical or some sort of mathematical formula that would take data that you've given it and then give you a suggestion or a prediction. That's essentially what it is. So at the most basic level, the simplest model you can build is say, I don't know, say X, say think of a simple maths formula, like, A plus X equals 2. And then, sorry, 1 plus X equals 2. 2 plus X equals 3. 3 plus X equals 4. You can start to deduce what X might be, right? So, and what we're trying to build essentially is something that we can give data to. It looks at the relationship between the data. For example, what I've just told you, like women may spend more on average on clothing items than men do. Those kind of trends or relationship, should we call it, is what the machine learning model or your predictive model is going to recognize by itself. And then next time, if I give it a woman's name or something, it will then guess how much she has to spend on clothing based on the 200 women's data that I've fed into it before and what they spend on clothing, if that makes any sense. So feature engineering is really identifying those things that are relevant to my machine learning model or my predictive model that will enable it to produce the right prediction. It's the process of translating raw data to better represent features. These features are then used to build better predictive models. First of all, do you understand what feature engineering is based on my 5-minute ramble in it? Because the next set of slides will require you to understand it. Oh, sorry. Yes, okay. Okay, we're gonna zip across. Yes, okay. We're gonna have to speed up a bit. There's quite a lot. So feature encoding. Feature encoding. I've described this. I've described what a feature is. So feature encoding should be logically easier once you understand what a feature is. So the simplest possible example is a table that has a column that has gender. Okay, so the gender could be either male or female. Encoding is essentially a way where we convert generally categorical variables. Categorical variables, like I described before, are things that are text essentially, that are not numeric. Yeah, the machine learning model or the model is just a mathematical formula. Think of it like that. So the model we're going to build, yeah, can only take numbers. It can only take numerical values. It could be a matrix or a vector or a tensor, but it just takes numbers. So we need to find a way of representing the text